something satisfies a strange coincidence in our sky, one so precise it almost feels engineered. The Moon, a rocky body roughly 400 times smaller than the Sun, sits roughly 400 times closer to the Earth. The result is that during a total solar eclipse, the Moon covers the Sun almost perfectly, edge to edge, revealing the ghostly tendrils of the solar corona in a spectacle found nowhere else in the known solar system. No other planet, no other moon, produces anything like it. If the Moon were slightly smaller or slightly farther away, totality would never happen. If it were slightly larger or slightly closer, the corona would stay hidden. The precision is breathtaking, and for centuries scientists dismissed it as pure coincidence. But here is where things get strange. The deeper we investigate our solar system, the more mysteries like this we find, patterns and oddities that seem to defy easy explanation. And one of them, a puzzle that has quietly haunted planetary science for decades, may be the greatest unsolved mystery in our cosmic neighborhood. It concerns something so fundamental that you would think we had figured it out by now, how the planets ended up where they are. Take a look at the solar system and everything appears orderly. Mercury close in, then Venus, Earth, Mars, the asteroid belt, then the gas giants, Jupiter, Saturn, Uranus, Neptune, all arranged in a neat progression outward from the Sun. It feels natural. It feels inevitable. But it is not. When scientists began building computer models of how the solar system should have formed from a collapsing disk of gas and dust some 4.5 billion years ago, they hit a wall. The models worked beautifully for the inner rocky planets. They worked for the general idea of gas giants forming farther out. But they could not reproduce what we actually see. The specific arrangement of the outer planets, their distances from the Sun, their orbits, even their slight tilts and eccentricities, none of it matched the straightforward predictions. Something was missing from the story. To understand why this is such a deep problem, you need to appreciate how planets are supposed to form in the first place. Imagine the young Sun, surrounded by a vast rotating disk of gas and dust, a protoplanetary disk stretching billions of kilometers in every direction. Within that disk, tiny grains of dust begin sticking together. Millimeters become centimeters, centimeters become meters, and eventually these clumps grow large enough for gravity to take over, pulling in more material, sweeping their orbits clean. This process, called accretion, is well understood for the rocky planets. But for the gas giants, there is a problem of time. Jupiter is more than 300 times the mass of Earth. To build a core large enough to start hoovering up hydrogen and helium gas from the disk before that gas dissipates, which happens within just a few million years, the planet needs to form astonishingly fast. And it needs to form in a region of the disk where there is enough material to work with. The original models placed Jupiter roughly where we find it today, around 5 times Earth's distance from the Sun, and Saturn a bit farther out. But Uranus and Neptune posed a genuine crisis. At their current distances, 20 and 30 times Earth's distance from the Sun respectively, the disk would have been so thin, so sparse, that building planets of their size should have taken longer than the age of the solar system itself. In other words, Uranus and Neptune should not exist where we find them. Not unless something moved them there. This realization, slow to crystallize but impossible to ignore, opened the door to one of the most radical ideas in planetary science. What if the solar system we see today looks nothing like the solar system that originally formed? What if the planets migrated? The concept sounds almost absurd at first. We think of planets as fixed landmarks, reliable markers in the vast emptiness of space. But orbits are not permanent things. They are the product of a gravitational negotiation between every massive body in a system. And when that negotiation shifts, when masses change or new interactions arise, orbits change too. In the early solar system, the planets were not alone. Beyond the orbit of the outermost giant, there existed a massive disk of icy debris, billions of small bodies left over from planet formation. A primordial version of what we now call the Kuiper Belt, but vastly larger and denser. And these small bodies, insignificant individually, collectively held the key to reshaping the entire solar system. Here's where the story takes a remarkable turn. In the early 2000s, a group of planetary scientists working in Nice, France, proposed a model so elegant and so unsettling that it became known simply as the Nice model. Their idea was this. In the beginning, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, formed much closer together than they are today, all within a relatively compact region between roughly 5 and 17 times Earth's distance from the Sun. Beyond them lay that enormous disk of icy planetesimals. For hundreds of millions of years, the system remained in a fragile equilibrium. The giants slowly interacted with the outer disk, exchanging tiny amounts of energy with the countless small bodies that drifted close enough to feel their gravity. Think of it like a gravitational conversation, each close encounter nudging a planetesimal inward or outward, and, by Newton's third law, nudging the planet ever so slightly in the opposite direction. Jupiter, being the most massive, tended to fling planetesimals outward, which caused Jupiter itself to drift slightly inward toward the Sun. Saturn, Uranus, and Neptune, lighter and more susceptible, tended to absorb the angular momentum from these encounters and slowly drifted outward. This was a gentle migration, a slow and quiet rearrangement over millions of years. But the Nice model proposed that this gradual shift eventually triggered a catastrophe. As Jupiter migrated inward and Saturn migrated outward, the two planets approached a very specific orbital relationship. Their orbital periods neared a ratio of 1 to 2, meaning Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. This is called a mean motion resonance, and in orbital mechanics, resonances are powerful things. Think of pushing a child on a swing. If you push at random intervals, not much happens. But if you push at exactly the right moment every time, the swing goes higher and higher. That is what a resonance does to orbits. When Jupiter and Saturn locked into this resonance, the periodic gravitational tugs between them amplified dramatically. The effects cascaded outward. Saturn's orbit became more eccentric, more elongated, and this destabilized the orbits of Uranus and Neptune. Within a shockingly short window, perhaps just a few million years, perhaps even less, the outer solar system descended into chaos. Neptune was likely flung upward, plunging through the dense primordial disk of icy bodies like a bowling ball through pins. The gravitational scattering was enormous. Billions of planetesimals were hurled in every direction, some inward toward the inner solar system, some outward into deep space, some into highly inclined orbits that would carry them far above and below the plane of the solar system. There is even evidence, still debated, that Uranus and Neptune may have switched places during this upheaval, with Neptune starting closer to the Sun than Uranus and ending up farther away. The scars of this event, the Nice model suggested, should be visible everywhere, and remarkably they are. A late heavy bombardment, a period roughly 700 million years after the formation of the solar system, when the inner planets were pummeled by a sudden surge of impacts, had long puzzled scientists. The Moon's battered face preserves the evidence in its ancient basins. Enormous circular scars like Imbrium and Orientale, dated to an era that seemed far too late for leftover planetary formation debris. The Nice model provided an explanation. Those impactors were icy bodies from the outer solar system, scattered inward by Neptune's violent migration through the primordial disk. The timing fit. The populations fit. Suddenly, a mystery about the Moon was connected to a mystery about the planets, and both were connected to a hidden chapter of cosmic violence that had been erased from the orderly solar system we see today. But the Nice model also explained something else, something subtler and in some ways more beautiful. It explained the Trojans. Jupiter has 2 large clusters of asteroids that share its orbit, one group leading the planet by 60 degrees and one trailing by 60 degrees, trapped in stable gravitational niches called Lagrange points. For decades, the origin of these Trojans was unclear. They did not look like main belt asteroids. Their composition seemed different, more primitive, richer in dark carbon compounds. The Nice model predicted that during the period of instability, as planetesimals from the outer disk were scattered in all directions, some would have been captured into Jupiter's Lagrange points, frozen in place as the chaos subsided and Jupiter settled into its new orbit. When NASA's Lucy mission began its journey to visit Jupiter's Trojans, one of its scientific goals was to test exactly this prediction. If the Trojans are indeed refugees from the outer solar system, Their composition should tell us what conditions were like in that primordial disk, offering a window into a world that no longer exists now. The NICE model is not the only game in town, and it has evolved significantly since it was first proposed. One of its challenges has always been the inner solar system. While the model does a remarkable job explaining the outer planets, the asteroid belt, and the Kuiper belt, the original version had difficulty preserving the inner planets during the instability phase. Mars in particular was troublesome. In many simulations, the gravitational chaos that rearranged the outer planets also destabilized the inner planets, sometimes ejecting Mars entirely or sending it crashing into Earth. This is, to put it mildly, a problem if you are trying to explain a solar system in which Mars clearly still exists. Refinements to the model addressed this by adjusting the timing and intensity of the instability, proposing that the chaotic phase may have occurred earlier than originally thought, perhaps within the first 100 million years rather than several 100 million years later. This version, sometimes called the early instability model, sacrifices the clean connection to the late heavy bombardment, but gains a more stable inner solar system. The debate continues, and it reveals something important about how science works. The NICE model is not a single fixed theory, but a family of hypotheses, a framework that keeps being tested, adjusted, and challenged as new data arrives. And one of the most fascinating challenges has come not from within our solar system, but from beyond it. Over the past 2 decades, the discovery of thousands of exoplanets, planets orbiting other stars, has revealed something that nobody anticipated. Our solar system is weird. Not just unusual, but genuinely strange compared to the galactic norm. The most common type of planet in the Milky Way appears to be the super-Earth, a rocky or icy world larger than Earth but smaller than Neptune, with an orbital period often measured in days rather than months or years. Many planetary systems are packed tight, with multiple planets huddled close to their star in compact resonant chains. Others feature hot Jupiters, massive gas giants orbiting closer to their stars than Mercury orbits the Sun. Our own system, with its small rocky planets close in, a vast empty gap, and gas giants on wide orbits far out, is a relative oddity. We may not be typical at all. This has led some scientists to wonder whether the instability described by the NICE model is not just a peculiarity of our solar system, but is in fact the event that made our solar system peculiar. Perhaps most planetary systems begin in tight, resonant configurations, and most of them stay that way. But in our case, something went wrong. The resonance between Jupiter and Saturn triggered a cascade of chaos that scattered the outer planets outward, cleared out the debris, and produced the wide, sparse, orderly-looking system we inhabit today. If this is true, then the very feature that makes our solar system hospitable to life, the spacing that allows a stable, temperate Earth, may be the result of a cosmic accident, a gravitational dice roll that most systems never experience. And this brings us to what may be the deepest layer of this mystery. There is something about our solar system that no model, no matter how sophisticated, has fully explained. It is the relationship between the system's architecture and the conditions that allow a planet like Earth to exist. Earth sits in the habitable zone, the narrow band around the Sun, where liquid water can persist on a planet's surface. But the habitable zone alone is not enough. Earth's long-term climate stability depends on Jupiter acting as a gravitational shield, deflecting or absorbing many of the comets and asteroids that might otherwise bombard the inner solar system. It depends on the Moon stabilizing Earth's axial tilt, preventing wild climate oscillations. It depends on the asteroid belt being just the right size, massive enough to have delivered water and organic molecules to the early Earth, but not so massive that it bombards us incessantly. Each of these factors traces back in one way or another to the dynamical history of the solar system, to the migrations, the resonances, and the great instability that rearranged everything. There is a concept in philosophy called the fine-tuning problem, usually applied to the fundamental constants of physics. Why is the gravitational constant exactly what it is? Why does the strong nuclear force have precisely the strength needed for stars to burn? The solar system presents its own version of this puzzle. Why did Jupiter and Saturn hit a resonance that scattered the outer planets just so? Why did Earth survive the chaos? Why did the right amount of water-bearing material reach our planet? Each answer generates a new question, and the chain of questions leads backward in time to the very first moments of the solar system's formation, to the initial conditions in the protoplanetary disk, to the density and composition of the molecular cloud that collapsed to form the Sun. We do not know why those initial conditions were what they were. We may never know, but we can trace their consequences forward across 4.5 billion years, and the story they tell is one of astonishing contingency, a chain of events in which tiny differences at the start could have produced a radically different outcome. Consider this: if the primordial disk had been slightly more massive, Jupiter might have migrated farther inward, potentially ejecting the inner planets entirely. If it had been slightly less massive, the giant planets might never have achieved the resonance that triggered the instability, and the solar system might have remained in its original compact configuration, with no wide-orbit Neptune, no scattered Kuiper belt, and possibly no conditions favorable for life as we know it. The solar system we inhabit, the one that feels so natural and inevitable when you look up at the night sky, may be balanced on a knife's edge of initial conditions. And the greatest mystery is not any single feature of this system, but the fact that all these features fit together, that the whole arrangement works, that we are here to wonder about it. When you look at the solar system through this lens, the neat textbook diagram dissolves into something far more interesting. What replaces it is a dynamic, violent, contingent history in which nothing was guaranteed. The planets are not where they were born. The debris fields are not primordial, but are the wreckage of a great upheaval. The order we see is not the starting condition, but the aftermath of chaos, a kind of cosmic scar tissue that healed into something beautiful and strange. We are still in the early chapters of understanding this story. The James Webb Space Telescope is now observing protoplanetary disks around young stars with unprecedented clarity, watching the process of planet formation unfold in real time. Missions to the outer solar system, to Jupiter's Trojans, to the icy moons, to the Kuiper belt, are gathering the forensic evidence we need to reconstruct what happened in our own system's deep past. And the continued discovery of exoplanets is placing our solar system in its proper context, revealing just how unusual it may be, and prompting us to ask whether that unusualness is meaningful. There is a humility in this investigation that feels important. A century ago, scientists assumed the solar system was typical, that most stars would be surrounded by similar arrangements of rocky and gaseous worlds. Now we know that is almost certainly wrong. Our system may be an outlier, shaped by a specific sequence of gravitational events that most planetary systems never experience. And the mystery of why our particular corner of the galaxy produced this particular arrangement, this particular sequence of planets, this particular world where water flows and minds wander, remains open. It is not just the biggest mystery of the solar system. In some ways, it is the biggest mystery about us. Because every question about why the planets are where they are is also, at its deepest level, a question about why we exist at all. And perhaps that is the most remarkable thing. But a species born on a small rocky world, orbiting an ordinary star, in a solar system shaped by ancient chaos, has learned enough to recognize the mystery. We do not yet have the final answer. We may not have it for a very long time. But we know the right questions now. And in science, knowing the right questions is how every great discovery begins.